So in an inverse relationship, what happens is that when one variable is multiplied by some number, the other variable is multiplied by the inverse of that number. Right? So what ends up happening is as one variable increases, the other variable decreases, and vice versa. As time increases, speed decreases, or you could say as time decreases, speed increases. Okay, now think about this. If the first variable, for example, is multiplied by 2, it's going to get bigger. What's going to happen is the other variable is going to be multiplied by the inverse of 2, or 1 over 2. Well, if you're multiplying by 1/2, the second variable is going to get smaller. Okay, so this is what's happening in an inverse relationship. Now I'm going to put some equations up, and we're going to look for inverse relationships between pairs of variables by looking at the structure of the equations that they are in. So here we are again, but this time we're looking at inverse relationships, and I'd like to throw a bunch of equations up on the whiteboard. All right, and again, we don't have to know exactly what all these equations and all these symbols mean. I hope you know some of them. It's a technique about looking at variables. All right, so it doesn't matter that we don't know exactly what all these equations mean, and we haven't worked with all these equations yet. Completely irrelevant to the discussion at hand. All right, so here we got our speed equation equals distance divided by time. Now remember before we had an equation where the gravitational, see the G? Gravitational potential energy. All right, now you might have heard of some of these symbols in maybe 8th grade or 9th grade physical science. All right, so you're not 100% completely unfamiliar with them. All right, but the gravitational potential energy is equal to the mass times the acceleration due to gravity of the celestial body that you're on. Celestial body meaning sun or planet or asteroid or comet or whatever, times the height. All right, now somebody will say to you, the way they're written right now, okay, mass is directly related to PEG, acceleration due to gravity is directly related to PEG, and height is directly related to PEG. We got that. But clearly, these guys here are inversely related to each other because they're on the same side of the equal sign and they're all in the numerator. But I prefer to get them on opposite sides of the equal sign to make these determinations. Right? It's personal preference, okay, not a big deal. So what I'm going to do is I'm going to divide by mg, all right, divide by mg, and I'm going to rewrite this equation, h equals, all right, over here, h equals PEG divided by m times g. All right, for purposes of my discussion here, I like to make the decision about how two variables are related exclusively when they are on opposite sides of the equal sign. All right, as you get better and better and more experienced at physics, then you're going to find other ways to do it. Okay, but I do prefer, if I'm going to decide how, for example, h and g are related, I want them on opposite sides of the equal sign. All right, just so I have some kind of a rule, you know, that I can go by. All right, so I've rearranged that equation. All right, now let's look at some other equations. We've got our equation here, v is equal to the square root of 2ke over m. We've seen that before. Okay, we've got fg is equal to gm1 m2 over r squared. All right, we've got fc is equal to mv squared over r. All right, we've got voltage, for example, is equal to work or electrical energy divided by charge. And that's enough for now for us to look at. Okay? So, how can you tell when what's one way that you can tell that two variables are inversely related? Okay, so again, I like to have the two variables that we're looking at on opposite sides of the equal sign. Now again, all right, this speed here is over 1. Let's use a a blue marker for that, all right, so we can see it better. This speed here is over 1, all right? Now, when they're on opposite sides of the equal sign, and one is in the numerator and the other is in the denominator, they're inversely related, as long as there's no squares or square roots. Okay, so you've got velocity here, speed, which is inversely related to time. Okay, look over here. Now, I'm going to call this, I realize that we've got the gravitational force here, and you've got the distance here, but it's squared. So this is going to be an inverse squared relationship. All right, we're going to leave that out for now. It is a type of inverse relationship because this is on top, this is on the bottom, but it's squared. So we're going to call that an inverse squared relationship. We'll look at that in just a couple of minutes. All right, so we're going to leave this out for now. All right, it's a type of inverse relationship, but it is inverse squared. Here, all right, this FC here is over 1. So this is in the numerator, this is in the denominator, okay? You've got an inverse relationship right there. All right, here, all right, this is in the numerator, this is in the denominator. You've got an inverse relationship between charge and voltage or potential difference. All right, so here we've rearranged this equation so that now we have H on the opposite side of the equal sign from M and G. All right, so now based on my little rule here, all right, when they're on opposite sides of the equal sign, and one is in the numerator, like here's the H in the numerator, right, and let's just say G, for example, is in the denominator, all right, you've got an inverse relationship between G and H. All right, and let me just talk real briefly about what that means in this case. All right, G is the acceleration due to gravity of, let's just say, some planet. All right, so when you have a small planet, let's say like the Earth, all right, let's call Earth a relatively small planet for the sake of this discussion. So G is small, all right, and H is some number, whatever it is, okay? Now, if you go to a larger planet, all right, let's say Jupiter, where G is bigger, okay? What this means is that in order for PEG and M to stay the same, okay, if G is bigger, then that means H, the height, right, has to be smaller. Okay, so again, this is an inverse relationship between H and G. Okay, and again, keep in mind, G means you're going to a different planet or you're changing your position relative to the same planet. All right, now, just very briefly here, you've got the speed here over 1, you've got the speed in the numerator, you've got the mass here in the denominator, so it is a sort of an inverse relationship. I mean, it definitely is an inverse relationship, but keep in mind it's not going to be quite as straightforward as these others because you've also got the square root sign there affecting how the speed changes. All right, it is going to be an inverse relationship because it's in the denominator. All right, this is in the numerator, this is in the denominator, but not as straightforward as these others because of the square root sign also. All right? Okay, so that's an inverse relationship. All right, now, let's do the same thing with inverse relationships that we did before with direct relationship and just do a little bit of math, okay, so that we can see exactly, quantitatively, how the numbers, how changing one number affects the other, how changing one variable affects the other variable if you have an inverse relationship. All right, so here we have our same nice simple equation, and we're looking at the inverse relationship that exists between time, all right, and speed. Okay, so we have to keep the distance constant. All right, so let's say that one person, right, however they manage to do this, all right, covers 24 meters, okay, in 3 seconds. Okay, so this person has covered, all right, this person's speed is 8 meters per second. All right, now, what if another person covers the same 24 meters in, it takes him more time. Takes him double the amount of time. All right, so the amount of time is doubled. the amount of time is multiplied by 2. What is this person's speed? Well, 24 divided by 6 is 4 meters per second. All right, so for an inverse relationship, all right, we said when one variable is multiplied by a number, right, comma, the other variable, the variable that is inversely related, the other variable is multiplied by its inverse. So the time, all right, watch this, the time was multiplied by 2, so the velocity was multiplied by 1/2. This doubled, this halved. All right, so you could say that. All right, for example, all right, let me erase this. All right, where's my? All right, you can copy that. You know, freeze the. I think you copied that before, right? Okay. So, for example, all right, example, when one variable doubles, comma, the other is halved. Okay? So that's your inverse relationship. Okay, now just real quickly the graph of an inverse relationship. All right, so here's the graph. Okay? Let's take a nice simple V equals D over T, where the variables that are inversely related are going to be the speed and the time. Okay? And what we're saying, all right, now here's our independent variable time. Here's our dependent variable speed, okay? And what we're saying is when the, all right, let's say when the time is small, the velocity is big, okay, inverse relationship. As the time gets bigger, right, the time goes this way to get bigger, the velocity comes down and gets smaller, all right? As the time gets bigger, right, as the time gets bigger, the velocity gets smaller. As the time gets bigger, 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 velocity gets smaller. And the graph looks like a curve, right? Something like that. Remember, this is a sketch. You know, I don't have any real numbers here. It's just a sketch. But an inverse relationship looks something like that. Okay? And as the time is getting bigger, the velocity is getting smaller. Okay? Now, for our last couple of relationships, I'm not going to go into quite as much detail, but here we go. Okay? So for inverse squared relationship, I'd like to show you a couple of equations that have an inverse square in them. All right? We've got FG equals GM1 M2 over R squared. We've got FE equals K Q1 Q2 over R squared. And we've got, not that one, hold on. No, all right, let's use here. M equals 2KE over V squared. We rearrange the kinetic energy equation. Okay. Is there one other that we could do? Get the V squared on the bottom somehow. Yes, okay. So we could also have, all right, if centripetal force is mv squared over r, right? We'd like the v squared to be on the bottom, all right, so we can clearly show an inverse relationship. All right, so I'm going to cross multiply, all right? So it's going to be mv squared times 1 equals centripetal force times r. All right, all I'm trying to do is get this v squared on the bottom, okay? And then I'm going to divide both sides by v squared. All right, so divide by v squared, divide by v squared. All right, and what we've got here is that m equals FCR over v squared. Okay? All right, m equals FCR over v squared. All right, so what you see here is that in every case, all right, you've got this dependent variable over 1. There's the numerator, there's the denominator, and it's squared. They are related as inverse squares, these two here. All right, this is over 1, this is in the numerator, this is in the denominator. These two are related in an inverse square manner. All right, right here, right, you got the mass, you got v squared, right, inverse squared relationship. Remember, inverse and squared. Inverse because you've got numerator, denominator on opposite sides of the equal sign, and it's squared. Numerator, denominator, opposite sides of the equal sign, and it's squared. Numerator, denominator, opposite sides of the equal sign, and it's squared. All right, numerator, denominator, opposite sides of the equal sign, and it's squared. All right, so these are all inverse squared relationships. Now, an inverse squared relationship is going to look, if you're not actually putting numbers in, it's going to look just like an inverse relationship. All right, it's going to look like that. Okay, it's going to look just like an inverse relationship. Okay, you would have to put numbers in there to see the difference between the two of them. All right, on a blank graph like that. All right, so that's all I'm really going to say about that one. All right, now I want to do exponential relationships. Okay, and again, my main focus here is that you look at an equation and you instantly know how all of the variables are related to each other. All right, if necessary, you do a little bit of rearranging. All right, so that you get them on opposite sides of the equal sign, because that's how I like to set up my rules. All right, not essential, but you know, it's just one way to have a nice rule that works all the time. Okay, exponential. I don't know why that made that E so weird. Exponential relationships. I don't know of any that are cubed. I mean, you could have a cubed relationship. These are all going to be squared relationships. Okay, so we've got kinetic energy is 1/2 mv squared. We've got centripetal force is mv squared over r. All right. Any others? Or something squared? Yeah. Here. Distance equals, now here, v initial t plus 1/2 at squared. But if the initial velocity is 0, okay, so if you're dropping an object, if the initial velocity is 0, then we can just put d equals 1/2 at squared. So let's do that. D equals 1/2 at squared. Okay, so what we have here, an exponential relationship where there's no inverse involved here, all right? So let's say, for example, the relationship here between kinetic energy and velocity, all right, is going to be squared. And remember what that looks like, all right? An exponential relationship, all right, where the independent variable is here. And notice it's not squared. This is just v. This is not v squared, all right? And ke over here, okay? That's going to look like this. It's going to be an exponential curve, okay, getting really fast, really high, really fast, okay? You've got an exponential relationship here, all right? That's going to look like that. If you put fc over here instead of the v, right? If you were to put t here, right? T here and distance over here, all right? You've got an exponential relationship between distance and time, all right, over here. Okay, so that's your exponential relationship. All right, you see this has an exponent, this has an exponent, this has an exponent, okay? And finally, square root, we'll just do square root. You're not going to see too much of this, but square root relationship. All right, square root relationship. Okay, very famous one. The period of a pendulum is 2 pi times the square root of L over G. Very famous square root relationship in physics. Again, this is the period, the amount of time it takes a pendulum to go forward and come back to the original spot. Okay? You've got our friend here, the kinetic energy equation, but solved for velocity, 2ke over m. All right, and let's throw in centripetal force. Let's see. Fc equals mv squared over r. Okay, we want to solve for v. Okay, so in other words, we want to solve for v, so we have a square root. Okay, Fc, I'm going to cross multiply, Fc times r equals mv squared. All right, divide by m. Okay, and then I'm going to flip it around. V squared equals FCR over m. Take the square root of both sides, bam, bam. So v is also equal to the square root of FCR over m. Okay, so we have a square root relationship, okay? A nice, simple square root relationship. Now, I'm not looking at the inverse here. I'm not looking at the relationship between period and g. I am not looking at the relationship between v, speed, and mass. I'm not looking at the relationship between speed and mass here. Those would be inverse relationships, even though they're under the square root sign. All right? What I'm looking at is when this variable here is on top, and this variable is on top and under a square root sign. Okay? On top, and under a square root sign. On top, and we could take FC or R. Let's take R. Okay? That's a square root relationship. Now, what does a square root relationship look like? Okay? I'll do this one right here. Okay? If you put the R here and the V right here, a square root relationship is going to look something like that. Okay, that's your square root relationship. That's for this one. If you want to do this one, all right, this is a very, very common, you will see this in a first year physics course. The L, the length of the pendulum, right, goes here, right, and the period of the pendulum goes there. Okay, so that's what the graph of a square root relationship looks like. All right, so what I've done, all right, let me just do a quick little, very, very quick little recap. We've talked about specifically what a direct and an inverse relationship means. In a direct relationship, when one variable increases, the other variable increases. Or you could say when one variable decreases, the other decreases. Basically, whatever happens to one variable, the exact same thing happens to the other variable. So for example, if one is doubled, the other doubles. If one is halved, the other halves. If one is tripled, the other tripled. That's your direct relationship. Inverse relationship, whatever number the first variable is multiplied by, the dependent variable is multiplied by the inverse of that number, which translates into if the first variable increases, the second variable decreases. or vice versa. If the first variable decreases, the second variable increases. All right, so that's direct and inverse. Now, we also looked at how to look at any equation, all right, and tell whether the relationship is direct, inverse, inverse squared, exponential, or a square root. All right. Now, keep in mind the way I explained that method is that I always take the two variables that I'm comparing and put them on opposite sides of the equal sign. And then all my rules apply to variables that are on opposite sides of the equal sign from each other. I always put the independent variable on the right side with a bunch of other friends, all right, and then the dependent variable, all right, the one that we want to see, well, what happens to him, all right, we put him on the left side, all right. I also looked at all 5 graphs, so you know what all 5 graphs are going to look like, all right. So relationships, when one variable changes, how does that affect another variable?